Yes, I hope my screen is visible as well as I am clearly audible to my participants. So before starting of the session, so I want to convey one thing that I suggest my participants, so if possible, you can sit with pen and paper. So since this session mostly, I think, will be related to mathematics, particularly probabilistics background. So if you sit with pen and paper, probably it may be much more helpful for you. So as I told in the last session that we discussed some fundamentals regarding artificial intelligence. So that I have not touched it for this part actually, probabilistic reasoning in artificial intelligence. So see here, so as you see here, mainly two keywords are here. So once we are going to discuss this session, one is probabilistic, second one is reasoning. Obviously, third one is artificial intelligence, that you know more or less some ideas on artificial intelligence. What it is, what is the advantages, disadvantages, or what are the various applications areas or research areas of artificial intelligence. So a little bit we are familiar with that. So here again two keywords is there. One is probabilistic, second one is reasoning. So already you know what is reasoning. Now first one probabilistic. So this is all about probability. So I believe that my participants are well aware about this probability, so that for the sake of starting actually, or for the sake of making it simple, so I will tell some facts or some ideas regarding probability, and quickly we'll come to our topics. So I hope that all of you knows probability. Based on that, we'll start this session. So see here, so how probability, the concept of probability, it is helpful in artificial intelligence. You know, the concept of probability has a huge significance, okay, in the framework of this artificial intelligence. You know, many of the machine learning algorithms that follows particularly this probability concept, once they are predicting or they are doing some classifications or some other works. So mainly they are dependent on this notion of probability. So this is my presentation sketch today. So initially we will focus on this Bayes theorem, then Bayes classifier we will focus, NIT Bayes classifier, and then slowly we will move towards this Bayesian network, and we will find out various research opportunities with this probabilistic reasoning. Now, as I told that this session, so the first word of this of my talk is probability. So obviously, I need to tell something regarding probability to set the tune for this session. Now, what is probability? I think needless to needless to tell that what is probability. So probability means, you know, the chance of occurring of a particular event. So those little bit who have forgot the concept of probability, so quickly we will revise it, and those who are comfortable, so again they will be immensely benefited from this concept. So as you know that what is the definition of probability? So here I have mentioned the definition of probability. Probability of happening an event A, if we say this is PA, so then what is the probability of PA? You know, number of cases favorable to A divided by total number of possible outcomes. So if we want to say more mathematically, then see, if an event can happen in m number of ways, okay, and fails to occur in n number of ways, then what is the probability of happening the event A? See what I am telling. The event can happen in m number of ways, and the event can fail in n number of ways. So what are the total possible ways? Obviously, total possible ways will be m plus n. Okay, because m, it can happen in this m number of ways, and it can fail in this n number of ways. So total number of possible outcomes, obviously m plus n. So what is the cases? So how many ways it may happen? So it may happen in m number of ways. This is the m number of ways it may happen. So what we are finding? Here we are finding the probability of happening an event A. Probability of happening or occurring or appearing an event A. Obviously, it may happen in m number of times, and total number of possible outcomes, it may be m plus n. In number of ways it may happen, n number of ways it may fails. So this is the total number of possible outcomes. That's why I told number of favorable cases to A, first one this. Number of favorable cases to A by total number of possible outcomes. So that is the definition of probability. Okay. Now, in which cases actually we need to apply this concept of probability? Here I have mentioned something. So probability generally, it is generally used, see, to predict the future of an event. Once we want to predict the future of a particular event in quantitatively, I am not telling in qualitative manner. We want to measure it quantitatively. We want to put some quantity behind it. Once we want to predict the future of an event, okay, with a certain probability of being correct. Now see the situation. So probability is used in such cases where the outcome of the trial is uncertain. Obviously, so here we want to predict that, okay, probability of appearing or probability of occurring, probability of happening an event A, favorable cases to A divided by, we want to say that total number of possible outcomes. Okay, this concept of uncertainty, all these things will come later in details. Now, this is probability. So probability of an event which is certain to appear, obviously that is one. Certainty is there, that event will appear, so probability is one. The probability of an event which is impossible, which will never appear, obviously that is zero. And I hope all of you knows this. If probability of happening an event is PA and that of not happening is PB, so obviously PA plus PB, it will be equal to 1. And you know what is the PA value of PA, quantity of PA, quantitative value of PA, so it will be in between 0 to 1. What about PB, probability of happening event B, also that will be in between 0 to 1. And obviously probability of happening an event and that of not happening an event, so if we take these two probability, the summation will be 1. So these are the very simple concepts, or I should say very fundamental concepts regarding probability that all of you know. Just to start the tune of this session, I am telling. Now see, so as I was telling that probability, the concept of probability. So if I say in this manner also we can define if PA, so probability of happening an event. So what is P not A? Obviously probability of not happening an event. So P not A plus PA we can write that is equal to 1. Where P not A, here I mean to say that is the probability of not happening an event. And what is PA equal to 0? PA equal to 0. What does it mean? Indicates that total uncertainty in that event A. And once I say probability equal to 1, obviously total certainty is there in the event A. Okay. Let us come. So these are some ideas which are going to be helpful once I will be delivering this session. Event. What is event actually? Each possible outcome of a variable is called an event. So many times I may utter the term event. So remember, what is event? Each possible outcome of a variable, we may say that is an event. Now, what is a sample space? Collection of all possible event is called the sample space. What is random variables? All these things we know. Normally, we'll use this random variable to represent events and objects in the real world. And these two are very important. Prior probability, posterior probability. In the definition itself, it is, I think, well defined actually, well explained. So it is prior, it is posterior. That means this is after. And first one is it is before. Prior probability. So the prior probability of an event, what does it mean? It is the probability computed before observing new information. We are computing the probability before observing new information. Prior means before only. So this is posterior, means after or next. So obviously this probability, so that will be computed after all evidence or informations are taken into account. Now see the situation. First one, before observing new information. And second one, after all the evidence or information you are considering. After that only this posterior probability we will compute actually. So obviously we can tell that this posterior, this probability, so this is a combination of prior probability as well as new information. So if we combine the prior probability as well as new information, so obviously it will give us this posterior probability. Again, these are a few ideas regarding probability. Quickly I will tell. Equally likely events. As you know, when the events are said to be equally likely, again it is self-explanatory only. Equally likely events. Equally likely. That means all events, or what I should say, that all events are equally likely here. All events are equally likely. What does it mean? All events are equally likely. That means none of the event cannot be expected to occur in preference to others. All they have an equal possibility to appear. See, if one of them cannot be expected to occur in preference to others. Okay. In other words, each outcome is likely to occur as any other outcome. Let us say some example. If we throw a die, then what will happen? All 6 faces. That means 1, 2, 3, 4, 5, 6 are equally likely to appear. Nice. Can I say that occurring of 6 probability will be more, occurring will be more? No, no. Likely to appear. Another one is this mutually exclusive or disjoint event. Mutually exclusive, disjoint, obviously. So we say that some set of events are mutually exclusive or disjoint if they cannot occur simultaneously. Mutually exclusive, so they cannot occur simultaneously. Only independently they can occur. Those examples are given again. So like that, I can say if we throw a coin, so head and tail. So is it possible that head and tail, I am throwing some coin, tossing some coin, and ultimately head and tail will occur both these things at the same time? No, this is mutually exclusive. If head is appearing, tail will not appear. If tail is appearing, head will not appear. Independent event actually. What is exhaustive events? So total number of possible outcomes of an experiment is called exhaustive events. As I was telling, if we are tossing a coin, that means either head or tail may turn up. So what is the possible outcomes? So possible outcomes are here 2 only. So it may lead to either head or tail. That means head or tail. So this belongs to the exhaustive events. So total number of possible outcomes of an experiment, we are telling this is the exhaustive events. Okay, now what is uncertainty? I think yesterday, or not yesterday, day before yesterday, today it is day 3. In first session, I told you something uncertainty. So that means when we say something is uncertain, something is not clearly defined, something is not precisely defined, some informations are not precisely given, something is unknown. Okay, so all these facts we consider belongs to uncertainty only. And you know that today the most important thing that I can tell, I think all you will be agree with me that most certain thing in our real life is the uncertainty. Can we ignore that? See what the statement I am making. The most certain thing in our real life today, day to day, it is the uncertainty only. Obviously, we cannot ignore it. It is a fact only. No one can deny it. But again, should we stop working or should we stop computation? Should we stop taking decisions in the arena of uncertainty? No, no. We should not stop. We should proceed. We should progress in spite of the presence of uncertainty. That means we need to deal with this uncertainty. That's why all these concepts are coming into picture. Now see, so here, what in the very first session, so we have got some knowledge representation. Okay, I've got some ideas on this using the first order logic and the propositional logic with certainty. So can you feel right now whatever I told in the very first session of first day of this FDP? I told some concepts of this propositional logic. I told some concept regarding this first order logic. Is there any uncertainties involved? or those things what I told, discussed that day, those belongs to purely certainty only. What I told, I can remember. So there is no uncertainty involved there. So cases were fully certain there actually. So so that only we discussed. So uncertainty manner we cannot discuss. But is it like that? That sometimes we may write A implies B. What is the meaning of this A implies B? Knowledge representation. So it is used for. So it means that if A is true, then B also will be true. A is true, B also will be true. Now, suppose you don't have sufficient information regarding A. I don't know that A may be true or false. I don't know. So I don't have sufficient information. I'm very much unsure about this A is true or not. Then obviously, can I decide what about B? Now see the situation. If A is itself uncertain, I don't have that much knowledge regarding A. I have to clearly ensure if this is true. I'm not sure about that. Then how I can predict B? So this is the uncertainty. You cannot avoid that. Now see, so this kind of uncertain situations, if it appears, so then your maybe whatever your first order logic or propositional logic you have learned, that may be very much, I think, difficult to work in this situation. So now, so the fact is now that we need to deal with this uncertain knowledge. So slowly we are coming to the point. So we need to deal with this uncertain knowledge, and wherever our knowledge representation techniques like first order logic or propositional logic are, I think, very much helpless at that particular point of view. Obviously, those things are some foundation, some pillars of artificial intelligence, but at the same time, with those things, it is very difficult to deal with this uncertain knowledge. So what do we do? What do we need to do then? Then only we need this uncertain reasoning, which is known as this probabilistic reasoning. Now, are you getting this point right now? So why probabilistic reasoning is very much important to know, and why it is very much, I think, very much significant factor of this subject, artificial intelligence. If we tell we know artificial intelligence, but we don't know probabilistic reasoning, perhaps we don't know artificial intelligence also. Because this kind of situation we can never bypass. This is closely related with our day-to-day life. So better to understand the concept of probabilistic reasoning to deal with those kind of situations. So these are the few causes of uncertainty. So many times for many causes may be there where uncertainty may appear. Now, probabilistic reasoning. So that is our point of discussion. Now, what is probabilistic reasoning? I hope now you are getting the point actually. So here the point I am writing, probabilistic reasoning is a way of knowledge representation. Obviously, it is a way of knowledge representation where, see, we apply the concept of probability to indicate uncertainty in knowledge. So note down this statement, whatever right now I am focusing. What is probabilistic reasoning in one sentence actually? Probabilistic reasoning, obviously this is a knowledge representation technique where you use the concept of probability to indicate the uncertainty in knowledge. Knowledge representation, representing the knowledge, that is very much, that in a very fast session you have seen it, how much importance it is. So this is the probabilistic reasoning actually. We can represent a knowledge using the concept of probability where there is uncertainty in knowledge. As I was telling, we use probability in probabilistic reasoning because it provides a way to handle the uncertainty. Okay, now uncertainty that may be someone's laziness or ignorance or maybe some information missing. So many causes will be there. In our real world, there may be number of situations, where the certainty of something is not confirmed. If I say it will rain today, so sometimes weather forecasting, we have seen so many things that weather forecasting, we see that today it may be in Warangal or Hyderabad, it may be, suppose weather forecasting is that heavy rains, but maybe in the evening or afternoon we will find out that not much rain is there. Where it was the weather forecasting kind of things. So where it is failing actually. So it is that it is once we are predicting or forecasting some things based on so much training or so much information we are forecasting something. But again, sometimes the forecasting or whatever also it may fail. That's why uncertainty is associated there actually. So it will rain today. So I don't know whether how much correct or opposite it is. So like that. So behavior of someone for some situations, match between two teams or two players anyway. So that means what is my point of concern that you cannot avoid the concept of uncertainty, and ultimately you need probabilistic reasoning to deal with uncertainty to represent your knowledge base. Yeah. So thus this is the need of probabilistic reasoning, as I was trying to focus on this part only in the last few slides. When there are unpredictable outcomes, can you avoid this unpredictable outcome? You can never avoid this. Once your source of information is uncertain only, then how you can avoid this unpredictable outcome? This is a quite part of your real life. When specifications or possibilities of predicates become too large to handle, when an unknown error occurs during an experiment, or whatever experiment we are doing, sometimes, as I was mentioning, that maybe knowingly, unknowingly, intentionally, or whatever, unintentionally, maybe some errors may be there in each and every research work. Okay, something will be there. Once we'll go for some big project or some big programming, something should be there. So that means, so if it is there, then obviously whatever the outcomes you are going to get, then outcomes also may become unpredictable. Now, so that is the need of this probabilistic reasoning. Okay, so to deal with this uncertain kind of nature, once you are solving some problems, so I think this concept of probability will be perfectly fitted, and it will help us to come out from these kind of situations and to make our life much more simpler. So mainly in probabilistic reasoning, mainly two ways are there to solve problems in uncertain knowledge. One is the Bayes rule, second one is the Bayesian statistics. Okay. Now, so before proceeding with this Bayesian theorem or Bayes rule, so we need to know one important concept regarding probability. So this concept is the conditional probability. Once a little bit we know or we are equipped with the probability, then what is conditional probability? No, you see, conditional probability is nothing. So on conditions, preconditions, some assumption is being applied. Conditional. That means we are dealing with the probability at the same time, some condition, some assumption, some restrictions are being applied. That is the conditional probability only. So what are the restrictions? The conditional probability is a probability of occurring an event when another event has already happened. Are you getting the fact? That I was telling earlier now that some assumption is there. What is the assumption? Some event has already happened. Some event has already appeared. Based on that, you need to find out the probability of occurring another event. One event has already appeared. It is known fact only. It is known fact. No uncertainty is there. It is appeared. It is known fact. So based on that, you need to find out the probability of another event. Let us say how mathematically we are defining it. So you may note it down actually. This is huge importance. One should be proceeding with this session. So let us assume that we want to calculate the event A when the event B has already occurred. See that term. We want to calculate the probability of event A, C, when event B has already appeared. So what we can write? The probability of A under the condition of B, or the probability of A given that B has already appeared. See, we can write it in this manner. PA by B. What does it mean, PA by B? We are computing probability of A given B. We are computing probability of A. Assumption is that B has already appeared. Try to understand it very clearly. Very carefully need to check it. So probability of appearing A once B is already appeared. B is given. You want to find out probability of A. So this is the joint probability of A and B divided by P. P of A by B. That means probability of appearing A where B has already occurred. Given B. Joint probability of A by B divided by probability of P. It is the joint probability, and obviously PB. This is the marginal probability of P. So see, similarly, what we can write? Can you write based on this? Can you write PB by A? What does it mean? PB by A? Probability of AP occurring B where A has already appeared. What it would be? Similarly, joint probability of A and B divided by probability of A. See, interestingly, so many interesting things will come from this side. So see, from here what we can write? So we can write, take it very carefully, what I'm writing. Probability, joint probability of A and B, what we can write? Equal to probability of A given B into probability of B. Can I write it or not? Yes, we can write it. So from here we can write, what we can write? Probability of A, okay, and B. That means joint probability of A and B equal to what we can write? Probability of B given A into probability of A. This is very much important throughout this session. That's why focusing more on this part. So now what we can now conclude? See here, this is also joint probability of A and B, probability of A by B into BB. This is also joint probability of A and B, probability of B by A into BA. That means, can you write? Can you write from these two things, from this one and this one? Both these things, can you write? Just take it very carefully. Can you write? If I write probability of A by B into PV, check it. Can I write it or not? Equal to probability of B given A, B by A into PA. Can I write it? Yes, we can write it because this is also P intersection B. This is also P intersection B joint probability. So PA by B into PB, we can write it PB by A into PA. So what the conclusion we can get it? So see what we can write. PA by B. So what we can write? P of B by A into PA, okay, divided by what we can write? PB. Can you write it or not? P of A by B, P of B by A into PA by PB. So simply see that based these two equations only I'm writing. This is simple mathematics. Whatever I have written now, that is nothing, but this is the Bayes theorem actually. This probability of A by B equal to probability of B by A into probability of A by probability of B. Whatever I have written now, so this is the known as this Bayesian theorem or Bayes theorem. See how we are coming probability. That's I told that conditional probability is very much important once you are trying to understand the concept of this Bayes theorem. Here I have given it actually. Okay. So more or less we are getting that what is Bayes theorem. Here also that it is there. I see. Here is also the same thing. Whatever I did earlier. So in this PPT, the same thing I have derived it actually. Probability of this is the joint probability of PA by B equal to this. So combining these two, this one and this one, can we write these things or not? Probability of A given B, probability of B by A into PA by probability of PB. So this is called this Bayes rule or Bayesian theorem. As I was telling, this equation is the basic of most modern AI system for probabilistic inference. That means you should never forget it. Okay, if you want to proceed with this today's session, so simply this you need to put in your brain permanently. You should not forget this. What is the Bayes theorem? Maybe I will write it in many different manner, but fundamentally, what is Bayes theorem that you need to understand before proceeding this session. And so this is, whatever Bayes rule allow us to compute the single term PB by A. How we are computing it in terms of PA by B, PB, and PA. So that's why, as I was telling, that this is very much useful in cases where you have a good probability of these three terms, and we want to determine the fourth one, obviously. Now, this is one example. So this is also Bayes theorem. Instead of A by B or B by A, here it is, you are writing it in using this cause and effect. So probability of cause given the effect. That means probability of cause given effect. So obviously probability of effect by cause into probability of cause divided by probability of effect. So this is simply, it is coming from this Bayes theorem. Yeah, so here something was there actually. So some mathematics was there. Simply we will avoid that. Okay. Now, as I was telling, so this Bayesian theorem, sometimes you may tell this is a Bayes rule, it is a Bayes law or Bayesian reasoning. Okay. So it relates, it is based on the concept of this probability, conditional probability, and also marginal probabilities up to random events. Now, how this name Bayes theorem came actually, Bayes theorem. So it was named with this British mathematician Thomas Bayes was there. Okay, who highlighted on this part. So based on the name of this British mathematician Thomas Bayes, the theorem also got the name. It is Bayes theorem. Okay, and let us compute something very quickly. Let us compute something so that here. Now, what is the probability? See that a patient has a disease meningitis with a stiff neck. Now see how this Bayesian theorem is helping us to predict something or to find out some probability. What is the question? What is the probability that a patient has diseases, meningitis with a stiff neck? Now, what's the data are given? Say, take it very clearly. A doctor is aware that disease meningitis causes a patient to have a stiff neck. See, doctor what is telling? A disease meningitis causes a patient to have a stiff neck, and it occurs 80% of the time. That means when there is meningitis, there may be stiff neck for 80% of the time. He is also aware some more facts. The known probability that a patient has a meningitis is this. Okay. Known probability patient has a stiff neck is this. Now let us see. Now let us consider this A with the proposition that the patient has the stiff neck and B with the proposition patient has meningitis. Are you getting the fact? Patient has stiff neck, we are considering this is A. Patient has meningitis, we are considering this is B. These two are variables, random variables only. So now what is given here? Patient have a stiff neck given meningitis. Already it is known to us or not. See, meningitis can cause a patient to have a stiff neck. This is 80%. It is known to us. That means patient have a stiff neck. Patient will suffer from a stiff neck if meningitis is there. Patient will suffer from a stiff neck if meningitis is there. So that is 0.8 given to us. It is known. Known probability patient has meningitis is this. So probability of this. That means probability PB, patient has meningitis. It is given. Known probability patient has stiff neck 2%. PA, what is PA? As you know, what is PA? PB means probability the patient has meningitis. PA means patient has stiff neck. What is PA? It is already given now. Patient has stiff neck equal to 2%. So all these things are given. What you need to find out? You need to find out probability of B by A. That means patient may suffer from meningitis if stiff neck is there. Now see the reverse situation actually. Patient may suffer from meningitis if stiff neck is there. What is the probability? Patient may suffer from stiff neck if meningitis is there. That is 80%. Reverse thing I want to find out. Patient may suffer from meningitis if stiff neck has appeared. What is the probability? So PB by A. What is Bayes theorem? PB by A means PA by B into PB by PA. So that is the Bayes theorem only. PA by B into PB by PA. So all these informations are already known. What is PA by B? Already known. What is PB? Already known. What is PA? Already known. So this. Very less only. That means here we can assume that one patient out of 750% has meningitis disease with a stiff neck. Here probability is very less. So are you getting the fact that using the concept of Bayes theorem, how we can easily predict something actually. In particularly here, the example I was showing in case of this disease diagnostics. Now let us slowly come to the fact this is naive-Bayes classifier algorithm. This naive-Bayes algorithm, this is a supervised learning algorithm actually, Bayes classifier. This is naive-Bayes classifier, I'll tell you. So it is actually supervised learning algorithm. You know what is supervised, what is unsupervised, maybe what is semi-supervised, what is reinforcement learning, because what I have seen that very first day, another coordinator, I think Manju Balamada, was trying to highlight on this fundamentals of machine learning. Maybe after that also a few resource persons have shared their ideas on this, so I'm not going through this. That means, so now this naive-Bayes algorithm, this is supervised learning algorithm, which is based on this Bayes theory. That means some training data set will be there, training and test cases will be there for this Bayes theory. Okay, so it is supervised Bayes classifier actually. I am telling this is a supervised classifier. So it is mainly used, so many, I think in many research works it may be used, but what I found most well-known application of this is text classifications that include a very high dimensional training data set. Okay, so it is a probabilistic classifier, which means it predicts on the basis of probability of an object. Don't forget this statement. It is a probabilistic classifier. Obviously, whatever the predictions it will do, all the predictions it will do based on the probability of an object only. And these are some other well-known application areas, spam filtration, sentiment analysis, and classifying articles. If time permits, I'll show you something there. Now, why it is called this naive Bayes? Why? Bayes theorem. So something here we are finding that some extra keyword naive, so that is preceding our this particular Bayes theorem or this Bayes concept, this keyword. So we can say that it is mainly composed of these two words actually. One is naive, second one is Bayes theorem. Now what is naive actually, let us say? It is called naive because it assumes, see, it's important, see, check it very clearly. It is assumes that occurrence of a certain features is independent on the occurrence of other features. Here once I will show you some example, maybe this fact will be very much clear for you. So all the features are independent, what I mean to say, on this naive Bayes classifier. All the features here will be independent. There is no dependency on these features. Now see here. Such as, so if a fruit is identified here on the basis of color, shape and taste, obviously, then if color is red, shape is spherical, taste is sweet, that fruit may be recognized as an apple. Now see here, so here each feature, what are the features? This color be one feature, shape be one feature, taste be another feature. Okay, and this is our class variable actually, that it is apple or what is there. So here, all these features, color, shape and taste, there is no dependency, all these are independent actually. Based on the color, we cannot conclude anything regarding the shape. Based on the color, we cannot conclude anything regarding the taste, or based on the taste, we cannot conclude regarding the color or shape like that. So here the features or the feature factors are totally independent. So this is the case for this naive Bayes classifier. What I should say, that what are the features, color, shape and taste, so all those are contributing equally, okay, to that particular class variable without depending on each other. So that's why this is called, this keyword is very much important naive. Now another keyword is Bayes. Obviously, it is dependent on this Bayes theorem. It depends on the principle of this Bayes theorem. That's why you are telling this is a naive Bayes classifier. Now, how this actually working condition of this naive Bayes classifier, how it works actually? I'll show you a few examples here. Now, suppose you have a data set, okay, weather conditions, and the corresponding target variable play. That means here this play is our class variable, and weather conditions is our feature vector actually. So what we are doing, see, so using this data set, this weather condition be our data set. So we need to decide that whether we should play or not on a particular day according to the weather condition based on the computation power of this knife gauge classifier. We have a data set weather conditions and the target variable, this is the class variable play. The data set we are having, that means we have given training to our classifier using those data set. Okay, now once some new features will come, then how your class variable will respond? Are you getting? So using this weather conditions, using these features and your class variable, you have trained your model, trained your classifier. Next one, test cases will come. Then obviously, so based on the training, it will put some outcome on your these test cases. Okay, let us see. Now, so in this kind of problem, what you need to do? So few things we need to follow actually. We need to convert the given data set into frequency table. And then we need to generate likelihood table by finding the probabilities of these given features. So firstly, we need to generate the frequency table. I'll show you how to generate it. Secondly, we need to generate the likelihood table. Wherever you will find out the probabilities based on the given features. Now you can use the Bayes theorem to calculate this posterior probability. So here what is your problem actually? So if the weather is sunny, then the players should play or not. So okay, not to be confused, let us say. So this is our data set. So this is your weather conditions actually, and this is your class variable or target variable. And this is our day number, 0 number day, first day. So total 2 weeks data we have collected as a training data. So 2 weeks data we have collected. So if it is a rainy day, okay, so play or not, yes. If it is sunny day, yes. If it is overcast, yes. Like that. So this data set we have collected actually. Okay, so this is our features, only one feature we have taken, and this is our class variable. So weather condition will be our feature here. So let us see. So how to, so as we told that initial step, this is a very simple example actually. Since only one feature we are applying, that is called weather conditions. It is not the case of multiple number of features are here. So initially what we will do, so we will generate the frequency table. That means, so I mean to say, how many rainies are there? How many overcast are there? How many sunnies are there? So based on that, you need to put up your frequency table. Just take it. So this is your frequency table. Say overcast, rainy, sunny. So once it is overcast, how many times yes was there? Once it is overcast, how many times no was there? See. Once it is overcast, how many times yes was there? So this is overcast, yes. This is overcast, yes, like that. This is overcast, yes. This is overcast, yes. Now check. So how many times? Check. This is 1 time, 2 time, 3 time, 4 time, 5 time. So 5 time overcast is there. Well as times I am finding yes for this overcast, no, 0. For overcast, no is 0 only. See, for overcast, yes is 5 times, no is 0 times. Similarly, for rainy, we are finding how many times it is yes, how many times it is no. Yes, how many times? Since three things are there only, overcast, sun, rainy, and sun. So this is, I think, yeah, overcast, rainy, and sunny. Three things are there. Okay, for each this overcast, rainy, and sunny, we are finding how many times it is yes, how many times it is no. So we are telling, so this is our frequency table. So from this frequency table, now we want to find out this likelihood table. So what will be a likelihood table? Here we find out the probability only, say. So this probability of overcast. So overcast no is 0, yes is 5. So what is the probability of overcast? So probability of overcast will be obviously, so it is 5 by 14 because total number, our sample space size is 14 only. Total number of possible outcomes may be 14 only. So what will be the probability of raining? So it is 4 by 14 only. 4 means these two plus these two. What is probability of sunning? 2 plus 3, 5 by 14 equal to this. Okay, what is the probability of no? So 2 plus 2, 4. 4 by 14 equal to this. What is the probability of yes? Check. 5 plus 2 plus 3, 10 by 14, 0.71. So we are finding all these probabilities. Actually, these will be helpful for you once we will start our computational process. Let us see. Computational process, let's start. See, we are applying Bayes theorem. So what we want to do? What is our objective? Let's see. So our objective is, if weather is sunny, then the players should play or not. That you need to find out. If the weather is sunny, then the player will play or not. That is our actually we need to find out. So that means we need to find out probability of yes by sunny, the probability of playing yes if it is sunny. Simultaneously, we need to find out probability of playing no once it is sunny. If probability of playing yes given is sunny is more, then the probability of no given sunny, if it is first one is more than the second one, then we can conclude that yes, you should play. Player can play the game on that particular day based on the training data set or based on the historical data. Now, it is a simple Bayes theorem, probability of yes by given sunny. So, how will you find out? Probability of sunny by yes into probability of yes divided by probability of sunny. Nothing else. This is Bayes theorem only. Do you know what is probability of sunny by yes? Do you know it? What is the probability of sunny by yes? Let us check. What is the probability of sunny by yes? This. What is the probability of sunny by yes? This check. Sunny is 3. So what is the probability of sunny by yes? 3 by 10. Just check it very clearly. Sunny by yes. Sunny is how many times? Sunny is 3 times. Sunny by yes. How many times yes? 5 plus 2 plus 3, 10 times. So what is probability of sunny by yes? Obviously it is 3 by 10. So that's why I'm writing it. Probability of sunny by yes equal to 3 by 10, 0.3. What is probability of sunny? Already you have computed 0.35. What is probability of yes? Already you have computed, that is 0.71. Check it. Probability of sunny, already you have computed 0.35, like that. What is probability of yes? Already you have computed 0.71. So now easily you can compute what is probability of yes given sunny. So this is the answer for that. Similarly, we need to compute what is the probability of no when sunny is given based on sunny. So this is the rules for that Bayesian theorem. I'm not repeating once again. Now all these things I am finding from this this table only, this likelihood table only. I'm getting all these informations. Probability of sunny by no. What is probability of sunny by no? Just check it. Probability of sunny by no. How many times? So this is probability of, this is 2. Probability of sunny. And sunny by no, this 2 plus 2 equal to 4. So probability of 2 by 2, 4 actually. This 2 by 4. Probability of sunny by no. What is probability of no? So this is 0.29. What is probability of sunny? 0.35. So what is the probability of no given sunny? 0.41. Which is more? Obviously, this one is more than this one. That means probability of yes by sunny given sunny is more than probability of no given sunny. So obviously, so if it is a sunny day, player can play the game. I hope now you are understanding the most simple application on this Bayes theorem. How we are solving a problem using Bayes theorem, which are very much relevant in artificial intelligence. What is the advantages of this Bayes classifier? Actually, many things are there behind Bayes classifier, but I am trying to focus on the main thing so that we can complete our next objective also. So this NIT Bayes is classifier, one of the fast and easily implementable machine learning algorithm to predict a class of data sets. We have seen how much simple or how much it is actually. It can be used for binary as well as multi-class classifications. Okay. Now, most important application for this NIT Bayes classifier is for text classification problems. Those who are working with this particular problem, text classification, maybe they will understand it better manner. Now, what is the disadvantages of NIT Bayes classifier? Can anyone tell what is the disadvantage of this naive-Bayes classifier? So see here, it assumes all features are independent or all are related. So it cannot learn the relationship between the features. Is it always that whatever the features will be there, all features will be always independent or unrelated? It may not be enough. Features also may have some strong relation among them. But simply your naive-Bayes classifier, it is ignoring or avoiding part of the relationship among all the features and assuming that each and every features are contributing equally to that particular domain. It is not considering that some features are contributing more, some features are contributing less. Obviously, it may be the case, na? So all the times, all features may not be contributing equally. So this is another research direction actually. If some features contribute more, some features contribute less, then what will happen? So that is one of the disadvantages of this naive-Bayes classifier. Now let us take some complex example. So this is our data set. So this example is a little bit complex, so that you can understand it much more better manner. Actually, the real life application of this naive-Bayes classifier started with a very simple example, slowly moving forward to the complex part. So here, how many features are there? Check. So this outlook, temperature, humidity, windy, all these are features. Play golf, this is our response vector, or we can say this is our class variable. Okay, so this outlook, temperature, humidity, windy. So instead of now single feature, now here we are finding that in this data set, a number of features are there. Here also we are collecting the information regarding 2 weeks, 14 days. Okay, so 14 days information we are collecting. Based on that, we need to decide whether someone should play golf or not. That is our objective here. Let us say. As I was telling, so this data set is divided into two parts. One is the feature matrix, second one is the response vector. Obviously, feature matrix means all vectors, data set. Okay, so vectors consist the value of these dependent features. Now, this whatever this outlook, temperature, humidity, windy, obviously all these are features, and response vectors, this contains the class variable. Class variable means this is the target variable. Here our target variable or class variable is play golf, yes or no. Okay, so this part already we told that the fundamental concept behind this naive-Bayes assumption. See, each and every feature makes an independent and equal contribution to the outcome. Here is the main complex part actually. In all the situations, it may not yield the equal contributions to the outcome. That the actual complexity will appear. Okay, so here we assume that since we are using naive-Bayes classifier, so simply our assumption is that no pair of features are dependent here. So simply everything is independent here. And as I mentioned, each feature has given the same weight. That means each feature we are considering at similar importance actually. Okay, so contribution of all these features are equal to this outcome. Now see how we are extending the Bayes theorem. Just check very clearly. So here we are working not with a single feature. Instead of that, we are working with a multiple number of features. We know Bayes theorem only for a single feature. If multiple number of features come into picture, then how we need to redefine the Bayes theorem? So from this slide, I think the concept will be very clear actually. So this is the Bayes theorem as we know, A by B, probability of A by B, probability of B by A into PA by PB. So this is our Bayes theorem. We all know very much well known about that. So obviously see here, PA by B, this is a posterior probability of B na, PA by B, obviously posterior probability of B. Okay, that means the probability of an event after evidence is seen. Okay, now let us see. So here, so if we write using this y and x, okay, then py by x, how we can write? Py by x, px by y into py by px. So this is nothing, make it simple. This is your Bayes theorem. Now we are extending. So here x is not simple single variable. Instead of single variable, we are dividing x into number of variables. See. Here, y is the class variable. That means we want to predict y. That's why we are telling this is the posterior probability of B actually. So y is our class variable, and obviously x is the dependent vector of size n. So that means we want to predict y based on this feature. Are you getting? We want to predict the class variable based on the given features. Features are already given. Okay, based on that, you want to predict that class variable. Here, these are the features you are mentioning. So that means x1, x2, x3 dot dot xn. So here we are assuming that our feature vector, whatever we are using, so our feature vector size is n as well. Okay. Now let us say. Now if we take, so from the data set, okay, if we take the first tuple, first row of this our data set, then what it will get? See, what is x here? In the context of our data set, what is x? Just check. In the context of our data set, what is x? X means the values only, na? Rainy, hot, high, false. This is the features and no, our class variable. X1 is rainy, X2 is hot, X3 be high, X4 be false. What is our y? Y equal to no. See, rainy, hot, high, false, no. Just check. Rainy, hot, high, false, your class variable is no. Just check here. So that means now instead of now we are working instead of a single vector, single feature, we are working with a number of features actually. Let's see. So how these features are contributing to this computational process. Let us see here. Okay. So let us come now. This is our naive assumption. See little bit we are here mathematically how we can write it. Just check it very clearly. Okay, so now we will split the evidence into some independent parts. Okay, so evidence, so that means here x1, this x, this is your evidence. So we are dividing the evidence into some independent parts. Okay, okay, so how we can divide it? Just check it. So now probability of y, given that x1, x2 dot 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 xn. So here what I mean to say, just take it very clearly. What I am telling here, this x1, x2, xn all are independent only. That means here how we can write. So this is probability of x1 by y into probability of x2 by y dot dot probability of xn by y into this probability of y divided by probability of x1 into x2 dot 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 xn. Since all these are independent actually, that's why the equation is coming in this manner. See how we are extending the Bayes theorem when the evidences are more actually. Number of evidences we have put into or more independent parts. Probability of y given x1 to xn. So probability of x1 by y into probability of x2 by y into dot 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 probability of xn by y into probability by Bayes theorem only now divided by this probability of x1 into x2 dot 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 xn. How we are simplifying? So taking this probability of y this side. Product of I equal to 1 to n probability of xi by y. Simple mathematics we are representing. Y we are keeping this side and this is x1 by y, x2 by y, xn by y we are writing in this form. Product of I equal to 1 to n probability of xi by y. Okay, and this is the term x1, x2 we are writing in the similar manner. So how we can write? So we can write in this format also. Probability of y into this product of I equal to 1 to n probability of xi by y. Just simply see here how this based on the concept of probability, how we are extending this Bayes classifier or naive Bayes theorem once we are getting a number of independent features. Then we need to apply these rules actually. Now here, so as I told, so this was initial our data set. Now you know, so for this data set, we need to compute the frequency table, we need to compute the probability, then you need to take some decisions. So that means frequency table you need to compute. One it will be for outlook, one for temperature, one for humidity, one for windy. Let's check. So one for outlook, one for temperature, one for humidity, another one for windy. Just check it how basically for sunny, how many times you're playing, how many times the class variable was yes, 2 times. How many times class variable was no, 2 times. So if you look closely here, then I think you can fill up this table. So for the sake of maintaining the time, so I am not here one by one, I am not computing. So directly here I have written there. So just you can get, if you go through the data set, easily you can get the frequency table. For overcast, actually 4 time it was yes, 0 time it was no. For rainy, so for outlook basically, so 3 times it was yes, 2 times it was no. So here easily we can find the probability. So what is the probability of yes? What is the probability of yes? What is the probability of no? Just check it, how we can. What is the total of yes? This is 2 plus 4 plus 3, that is 9. What is the total number of no? It is 5. So probability of yes, sunny, see that, probability of sunny by yes, obviously it is 2 by 9. Yes, on the overcast, it is 4 by 9. Are you getting how these values are coming? Probability of yes for this rainy, it will be 3 by 9. So all these things are coming, all this is a very simple concept of probability by which you are getting all these values. So probability of no, how it is coming, just check probability of no. How many times it was no? 3 times. What is total number of no? 5 times. So it is 3 by 5, like that. All these values are coming. Similarly, we are computing the values for this temperature also. So once you go through all these things, then easily will get it. So if we again go back to the table, it will take some time. So I am just trying to show you that the way we are computing it, and I hope easily you are getting it. Simply for temperature, it is hot, mild, and cold. So how many times hot was? Yes, 2 times. How many times hot was no? 2 times, like that. It was hot, but playing that your target variable was no, 2 times. It was hot, but target variable was, sorry, it is hot. Target variable is yes, 2 times. It is hot. Target variable is no, it is 2 times. It is mild. Target variable is yes, 4 times. It is mild. Target variable is no, it is 2 times. Similarly, others. So how many times total number of yes? 9 times. How many times total number of no? It is mentioning 5 times. I checked. 2 plus 4 plus 3, 9. 2 plus 2 plus 1, this is 5. So similarly, we can find out now this probability of yes. This is 2 by 9. Probability of this mild here, it will be 4 by 9. So similarly here we can find out the probabilities based on this frequency table. So once you are having all these probabilities and we have the expression, then nothing is there. Then easily, I think we can move forward. Simply, we can write these values in this expression and our job will be done. Now see. So here we have taken these features variables. That means this is the conditions: sunny, hot, normal, false. Outlook was sunny, temperature was hot, humidity was normal, and windy is false, no windy. So that features we have considered, and this is our feature values. Okay, so if this is the case, then you tell me that what is the probability of playing golf? So you should play golf or not, if this is the situation. So now easily we can find out now what is probability of yes by today, and we can find out what is probability of no by today. What is probability of yes by today? Today means what? Today means sunny, hot, normal, false. Oh, what is yes by today? Sunny outlook by yes, check it very clearly. Hot temperature by yes, because today means it is sunny, hot, normal, false. Based on Bayesian theorem. So sunny outlook by yes, hot temperature by yes, normal humidity by yes, no wind by yes, into probability of yes, divided by probability of today. Similarly, what is probability of no by today? See, what is today? Today means the same set of data, na? Sunny, hot, normal, false. Similarly, sunny outlook by no, hot temperature by no, probability of normal humidity by no, probability of no wind by no, into probability of no divided by probability of today. So these two things probability we need to compute. Let us compute. So all values are there in the table. No need to do anything. If you have derived the table, all values you will get from the table only. So here we are getting all these values from the table. Probability of yes by today, all values you will get from the table. So this is like suppose this one. What is probability of no by today? This one. But as you know that probability of yes by today and probability of no by today, if you do the summation, so it should be always 1. This is the rule of probability only. But since here probability of yes by today and probability of no by today is not equal to 1, so we need to do the normalization actually. So here we have done the normalization here, and again we are finding probability of yes by today divided by probability of no by today. That means obviously the predictions for playing wolf, that is yes only. So this is a typical applications that how we can apply this NIT-based classifier when number of feature vectors are many and to solve some problem. So here I'll restrict myself on this Bayesian classifier side. Actually, a number of things are there on this Bayesian classifier. So quickly we'll take a overview of this Bayesian classifier for just for 5 minutes. Then once again we'll start this Bayesian network, because Bayesian network, once this is a different concept. Obviously, it is also based on this Bayesian theorem, but little bit here concept is more difficult. So quickly, we'll take an overview of this, I think, this Bayesian classifier, so that once again, things will be very much clear. What I told, now you have seen that what I told for this Bayesian classifier. So these are our training records, So, and this is our testing data set. Okay, so here these are training sets, and this is the testing set. So if it walks like a duck, then it's probably a duck. So this is our training and this is testing data set. Now here, so that I told that for this actually this Bayesian classifier, so this is one of the obviously this statistics classifier actually. And foundation of this Bayesian classifier, obviously, it is Bayes' theorem. And all these assumptions already you have seen. Classes are mutually exclusive and exhaustive. Attributes are independent given the class. So that already we have seen. And already we know the concept, what is mutually exclusive and what is exhaustive. Now let us, as I was telling, that suppose this air traffic data is given to you. Okay, so see here. So what are the attributes? So this is days, season, fog, rain, all these things, and this is your class variable. Okay, and these are the values, attribute values. If it is a weekday, if it is spring, no fog, no rain, then your flight will run on time only. So this is some data, air traffic data that is given to you. So in this data set, you have 4 attributes: day, season, fog, and rain, and we have 20 tuples. Okay. And now, what are the categories of the classes? So here, here category of multi-classes are there. It is on time, late, it may be very late, it may be cancelled, all these things are there. Okay, now, so what we have given, we know. So we have some knowledge, now. We have some knowledge of data and classes. If features are that, classes may be that. And based on that, what you need to find? See, we are to find most likely classification for other unseen instance. Okay, so like that. If I provide some unseen instance, unseen features, then you need to predict, okay, that what will be that particular, what will be the category of the classes for these unseen data sets. So this is, as I was telling, so this is the actually classification. So that Bayesian classifier, as I was mentioning, that Bayesian classifier, in many applications, the relationship between the attributes and the class variable is non-deterministic. A test cannot be classified to a class level. So simply, you cannot say that probability is 1 for this. Rather, you can predict it. In this, we are providing some training data, and you are testing your system using some testing data. Then here, since we need to, what we can do? So in the most certain manner, if you cannot tell that this may be the situations. Okay, so here better that in these cases we'll go for this probabilistic. So that's why in such situation, the classification can be achieved probabilistically actually. Once some uncertain situation is there, then obviously you need to go to this probabilistic manner actually. And as I was mentioning, this Bayesian classifier that use this Bayesian theorem of probability for this classification purpose. So all these ideas already, as you have seen, so I'm not coming to this actually part. So now here, one important concept is there that is called total probability that I will come at right time. Okay, so here again some examples are there. Okay, let me avoid these examples. So if time permits, I will show you all these examples. Okay, so let me move to this Bayesian network part. So I hope that you have a little bit concept regarding this Bayesian classifier. So let us move to this Bayesian network. What is Bayesian network actually? See, here again two things are there. One is the Bayes and second is the network. You know what is the network? Network means obviously some set of nodes, some set of arcs or edges will be there. Okay, so that some graph network means we can tell some graph kind of things may be there. As you know, what is a graph? Graph is a collection of edges and nodes. Now, sometimes it may be directed, sometimes it may be undirected, sometimes it may be cyclic, sometimes it may be uncyclic. But you remember that Bayesian network, whatever you are going to discuss, that is a acyclic, and this see. What this is an acyclic graph. Okay, acyclic and directed graph, this Bayesian network actually. The Bayesian belief network, key computing technology for dealing with probabilistic events to solve a problem which has an uncertainty. Again, Bayesian network we are using to solve the problem regarding uncertainty. As I was telling, uncertainty, whatever problem you want to solve, so which is uncertain, the concept of probability will be there. And this Bayesian network that we are defining as a probabilistic graphical model. So here we have a set of variables, okay, set of variables and their conditional dependencies that we will define using a directed acyclic graph, as I was meaning to say earlier. Here network means you are considering a graph. Graph may be cyclic, graph may be acyclic, graph may be directed, graph may be undirected. But here, once it is Bayesian network, just keep it in your mind. It is a directed and it is a cyclic graph. No cycle should be there. And obviously, it is a directed graph. Here we are considering that, as you know, as I mentioned earlier, graph means some set of nodes, some set of edges connecting the nodes. Here nodes are our variables. Nodes are our random variables. Okay. And the edges, what are the edges? Connection between two nodes. I mean to say those edges, here we are considering as a conditional probability. Okay. So sometimes this Bayes network, we can tell Bayesian network, belief network, decision network, Bayesian model. So number of names are there for this. So this is mainly built from probability distribution. Okay, let us come to the part actually. Okay, now what is the purpose of using this Bayesian network? So it can be used for prediction purpose, anomaly detection, diagnostics, and many other things, time series prediction, decision making it uncertainty, many other applications we can use this Bayesian network. And here, most interestingly, before proceeding, I will tell you some example of Bayesian network and how we are solving problem based on the conditional probability table using the concept of Bayes theorem. Now, see the interesting part here. Let us try to understand this example in very clear-cut manner. Once you understand this example very clearly, then you may feel that almost you have got it, this Bayesian network. And I can tell one thing before proceeding, then today you find out in NET, you search in Google, you search in Springer, ACM, multiple transaction, Science Direct, whatever you can search. But you will not find out that much work on this Bayesian network actually. Bayesian network is very much complex. Few constraints are there. Researchers are continuously working on this Bayes network to solve some problem. But recently we have started that to do some experiment on this Bayesian network. Now, once I'll proceed, you may get to know the complexity. So this is a very much interesting. Some review papers I have studied where they have written a so much scope, the research scope using this Bayesian network, because it is not that much, not that much experimented, that Bayesian or scopes are Bayesian network. So that means if you can write some paper on this Bayesian network or do some good experimentation, then possibility is higher. So it may be accepted actually. So let us try to understand. See here, Harry installed a new burglar alarm at Harry installed a new burglar alarm at his home to detect the burglary kind of events. Okay, very good. So the alarm reliably responds at detecting a burglary, but also responds for minor earthquake. Harry installed a new burglar alarm. What is the purpose of that? To detect burglary, an illegal entry, unauthorized entry to his house. What this alarm, it will respond obviously. Once burglary is there, it will respond. But sometimes it will respond when there is a minor earthquake. Now, Harry has two neighbors. One is David and Sophia. So this is very nearby to this Harry. These two neighbors, Harry has, one is David, second one is Sophia. Now, who have taken the responsibility to inform Harry at work when they hear the alarm? See, because Harry may be at office for his or her work. Now, David and Sophia. So this is very nearby. These are neighbors of this Harry. And who has taken the responsibility that to inform Harry when they hear the alarm? Okay, fact is very clear. Now see the situation. So David calls Harry when he hears the alarm, but sometimes he got confused with the phone ringing and calls at that time. Now see the situation. What is the problems with David? David called Harry obviously once he heard the alarm, but sometimes he got confused actually. The phone is ringing and he is feeling that, okay, alarm is ringing, confused. And at that time too, he calls Harry. Now see. On the other hand, Sophia likes to listen high music and sometimes she misses to hear the alarm. That means all they have their own individual inherent difficulties. This is the part of real life, every one of us having some difficulties. Okay, now, so we would like to compute the probability of burglary alarm. See how many constraints are here in this particular problem. And in spite of this presence of all these constraints, we want to compute the probability of this burglary alarm. How to do that? Let us come to that part. What is your problem? Problem is there. Calculate the probability that alarm has sounded, but there is neither a burglary nor an earthquake. And David and Sophia both called Harry. We need to find out, see the situation here. We need to find out the probability alarm has sounded. Alarm has sounded, but there is no burglary, no earthquake. And David and Sophia both called Harry. See how much interesting and how much complex problem it is. We want to find out that probability. Here it is the uncertainty actually. That's why it is probability. Here it is not 100% sure, means probability is 1. Okay, 100% false means probability is 0. This is not that kind of case now. Fully uncertainty is there. That's why the concept of probabilistic reasoning is coming into picture. If it is 100% sure, why probability? You can say this is 1 only, sir. Otherwise, it may be no. But probability means obviously in between 0 and 1. Now let us see how to solve this problem. See, now we'll find out the Bayesian network for this above problem. Now see. Now let us come to that network actually. See, this is the network. This is the Bayesian network. See actually. So firstly, this is a graph. Secondly, this is a cyclic graph. And thirdly, this is a directed graph. That's why this is Bayesian network or Bayes network. See. So this is one variable, burglary, putting one node. Earthquake is another variable. Alarm, all these events are keeping as a variables. Okay. And as I mentioned, age means it is conditional probability. Here we are finding some table. These tables are known as conditional probability table. As already you know what is conditional probability. In short form, these tables we say this is the CPT, conditional probability table actually. See here. So here this probability you may find, sir, how we are computing this probability. Believe me, I am not computing any probability, assuming these are the known ones given. Okay. Okay, so this burglary, true, 0.002. Burglary, false, 0.998. That means probability of burglary true very less, probability of burglary false much more. As you know, so if you take summation of these two, that must be 1. As you know it now, so this is the rule of probability actually. So here, earthquake is true. Minor earthquake I am telling. So this is 0.001. Earthquake is false, 0.099. If you know one thing, easily you can find out another things also. Now this is the alarm cases. Maybe sir, you may be surprising. This in alarm, how so much probability is there? Because in alarm, it has two parent nodes. See, B and A. These two are parent nodes of this alarm A. Okay, and D for D and this Sophia calls S. So this is the parent node. You're getting the concept of parent node. So B and E are a parent node of A. A be the parent node of D and S. Okay. Now here one important concept is there actually. In conditional probability table, see, in each row in CPT sum must be 1. Obviously, because all entries in the table represents an exhaustive set of cases for the variable. So sum must be 1 only. In CPT, see that a Boolean variable with k Boolean parents contains 2 to the power k probabilities. See, Boolean variable with k Boolean parents, obviously it will contain 2 to the power k probabilities. See, hence there are 2 parents, so then it will contain 4 probability values. Now see the situation. So for alarm, how many parents are there? 2 parents. Burglary is. That means how much cases will be there? 2 to the power 2. So 4 cases will be there. So what are the cases? Burglary may be true. Alarm may be true. Now see. Sorry. Burglary may be true. Earthquake may be true. What is the probability? Then alarm is also true. If burglary is true, earthquake is true. What is the probability? Alarm is true. Let us assume it is 0.94. So what is the probability alarm is false? 1 minus 0.94, 0.06. All are mutually exclusive that I told an exhaustive set of events. Initially it is written just see. This exhaustive set of cases actually. If one occurs, another will not occur actually here. Okay. So similarly, see, since parents are 4, so 2 to the power 2 cases, 4 cases will be there. So burglary may be true, burglary may be false. If burglary is true, earthquake is false. What is the probability alarm is true? 0.95. What is the probability alarm is not true? This. If burglary is false, this earthquake is true. What is the probability? Alarm will be ringing 0.31. What is the probability? Alarm will not be ringing 0.69. Are you getting the fact? So these values are given. So here for the sake of simplicity we are considering. So these are the known values to our problem. So all these probabilistic values, whatever I am telling right now, so these values are all known values. Okay. So for this node D, so only one node is there, 2 to the power 1. So 2 cases will be here. So that means okay. If alarm equal to true, then probability of David calls true 0.91. Alarm equal to true, probability of David calls false 0.09. Alarm equal to false, probability of David calls alarm equal to false, probability of David calls also false 0.95. Just try to check it. So this 0.91 plus 0.09 summation will be 1. 0.05 plus 0.95, summation will be 1. All these are coming from basic probability science. Similarly for Sophia. Okay, this alarm. True, false. If alarm is true, probability of Sophia calls this. Probability of Sophia not calls this. If alarm equal to false, probability of Sophia calls this. Probability of Sophia not calls this. Here, almost all the values I am not taking it randomly. So obviously all the values have some meaning actually. Randomly nothing is taken. They are based on the, I think, so the values are already, obviously we have given the values in some meaningful manner actually. Okay, let us proceed with that. That means all probability values or probability tables are given here. Okay, next what you need to see. So what are our events actually? Our events are burglary events. Okay, so these are events: earthquake, alarm, David call, Sophia calls. Okay, so now this joint probability, see, probability of D means David calls, S, Sophia calls, A, alarm, B, burglary, E, earthquake. So how we can write it? So if you have a good knowledge of probability, so probability of D, S, A, B, E. So probability of D by S, A, B, E into probability of S, A, B. So it's a probabilistic idea only. So now how we can write it? See, this is now probability of D. Now, D means what? David calls. So David calls depends on what? I'll show you all these things as David literacy. David calls depends on alarm only, na. Sophia call depends on alarm only. That's why. Probability of D by A. David calls depend on alarm. Sophia calls depend on alarm. Probability of alarm depends on burglary and earthquake. Now it's getting a little bit clear. Into probability of burglary into earthquake. Okay, now let me come to this part, then it will be very much clear. The joint probability distribution, that we have some good idea on this joint probability distribution to move forward, to proceed forward actually. So just no need to understand anything, just to see these things. In general, for each variable xi, we can write the equation as C. How we can write? P of xi, given that xi minus 1 dot 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 to x1. So it is like that. Probability of xi, given that parent of xi. That means probability of xi, it will depends on its parent's nodes only, na? Probability of a node, how it will behave. Probability of a node, always it will depend on the parent node. If I'll show you a few examples. So probability of a node, obviously, this is probability of node xi. So it is depends on the parent node, as I was mentioning. See, probability of alarm depends on burglary and earthquake. Probability of David calls depend on alarm. Probability of Sophia calls depends on alarm. Probability of a node, obviously, it will depends on the parent nodes. Let us try to make some good idea from here, then it will be very much clear for us. So consider a problem with 3 random variables. Okay, let's see, A, B, and C. Let us assume that A is dependent on B and C is also dependent on B. Okay, so how we can write? C. So A is conditionally dependent on B. How we can write? Probability of A given B. C is dependent on B. How we can write? Probability of C given B. This way you can write. But here, see, A and C have no effect on each other. A and C are totally independent actually. A is conditionally independent from C. So this probability of A given B and C, what it will result? It will result probability of A given B only. Probability of, because A and C are not independent to each other. These are totally different actually. Probability of C B by A. So probability of C given B and A. C is not depending on A now. C is depending on B only. So it will result in probability of C given B. I will show you. Just take it very clearly here. Just see. In this node C. So we can rewrite C. Joint probability of A and C given B. Just take it. Probability of A and C given B. How we can write it? Probability of A and C given B. Probability of A and C given B. Obviously, we can write it. Probability of A given B into probability of C given B. Can we write it or not? Now, what will be the joint probability of this probability of A, B, and C? How we can write it? So let us write joint probability of A, B, and C. How we can write? Obviously, probability of A given B, probability of C given B into probability of B. No other things will be there. Now see, this B is the parent of A, C is the parent of A. Sorry, B is the parent of A, B is the parent of C. That's why A and C both depends on the parent B, but at the same time, parent B is independent. That's why separately we are writing parent B. So if you have a good knowledge of this, then writing all this formula is very much easier. Again, here I was trying to show something. If these two random variables are dependent, see, X and Y are dependent, then probability of X given Y, probability of XY by Y. You know that if these are dependent, probability of X and Y are dependent only, then you can write. If they are independent, then what we can write? Independent, no dependency relations on X and Y. Obviously, probability of X given Y equal to probability of X. Try to understand these two things. Once random variables are dependent, once random variables are independent. What is the difference between these two? And this is your total probability formula. You know, this is your total probability formula. Just give me 1 minute. Sir. Hello. 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 Hello, sir. Hello. Hello, sir. Yes, please. OTP is then generated after some time. Okay, it must be after 5 o'clock. After 5 o'clock. Actually, I am not there. After 5 o'clock, please generate. After 15 minutes. No, after 15 minutes, please. Wait. Okay. Yeah, so what we were discussing, so I hope I am audible. So what I was discussing, so this is our total probability formula. So what is our total probability formula actually? So this is probability of A. So I hope maybe you know this formula. Probability of A. So probability of E1 into probability of A by E1, probability of E2, A by E2, probability of E3 into probability of A by E3. So we can write this probability of A in this format. Probability of E1 by A by E1, this E2, A by E2, E3, A by E3, like that. Now see. তাহলে আমি একটু পরে কল করছি, হ্যাঁ? So now this is our problem actually. So see, calculate the probability that alarm has sounded, but there is neither a burglary nor the earthquake occurred, and David and Sophia both call Harry. So since now we have a good knowledge on this probability side, we can solve these problems. Actually, if you have a good knowledge on this Bayesian network, you can solve a number of problems regarding to these various situations actually. So here, what is the situation? Calculate the probability. Alarm has sounded, see. Alarm has sounded, but there is neither a burglary. Burglary is not there, okay? Nor an earthquake occurred. And David and Sophia both called Harry. Let's mathematically how we can do that. See. So alarm has sounded. Okay. This is alarm has sounded. Okay. And this David and Sophia both called Harry. That's why. This Sophia and David both called Harry. Alarm has sounded. Okay. But there is neither burglary nor a burglary nor a earthquake, but David and Sophia called both called an alarm ring. Alarm has sounded. So this is a joint probability. Now how to compute it? Just check. So this Sophia depends probability of this Sophia. What is this? Sophia depends on alarm. David depends on alarm. Can you remember that what Bayesian network? Sophia directly depends on the alarm. David directly depends on the alarm. That's why Sophia given alarm, David given alarm. Alarm depends on this burglary and earthquake. You can remember it. Alarm depends on this burglary and earthquake. As you can remember here, if I draw it, then alarm was at middle, and here it was burglary, and this was earthquake. Okay, so this is burglary, this is earthquake, this is alarm, and this may be David, and this was Sophia. So our Bayesian network was like this. And here now this. So that means David depends on alarm. This. So parent node of David is alarm. Sophia also parent node is alarm. Now for alarm, this parent node is B and E. That's why. Alarm, given that this is no burglary, no earthquake. Since there is no burglary, no earthquake. Okay. Into, so see, this probability of no burglary into probability of no earthquake. Now see how we are computing actually this kind of situations, then where alarm has sounded, Sophia David called, but no burglary, no earthquake. So not only this situation, see here. So based on this, we can compute the probability of a number of cases, of a number of situations. So here, what will be the probability? So probability here easily we can find. Now, here probability easily we can find. So because all these values are already given to us, probability of this S by A, all these are given in that particular table. Let us see. So probability of this Sophia, okay, probability of Sophia, this given alarm. So why it is 0.75? Probability of Sophia given alarm. Let us see here. See, probability of Sophia given alarm. So probability of Sophia calls given alarm. That means Sophia calls. Okay. Sophia calls true. Once alarm equal to true, 0.75. Probability of Sophia. That means Sophia is to call, Sophia calls true, where alarm is true. So that is 0.75. Like that, all values you can find out from this table on. Okay, all values you will get from this table only. So this is the probability. So see how much less is the probability. Because alarm has sounded, but neither burglary nor earthquake. Again, David and Sophia both called Harry. Like that, Bayesian network can answer any query about the domain by these joint probability joint distribution ideas. See the powerful nature of this Bayesian network actually. Whatever today we have seen, This is a very simplest case of Bayesian network, but obviously it is that much powerful that it can answer any query, okay, in this domain using the formula of disjoint probability distribution. And I should tell that, so this Bayesian network, it was proposed by Parle in 1980s. And obviously it is used for disposing the uncertain information in the context of particular AI. So long back it was introduced 1980s, but again I am telling that there is not so much research work, maybe due to the complex nature of this domain, maybe something else. So there is a huge opportunity to do some contribution in this particular domain actually. So Bayesian network, it is a basically way of uncertain knowledge representation, okay, and reasoning with the basis of probability and the graph theory. If you have a good knowledge of this knowledge representation, obviously you are having, and if you have a good knowledge on probability and graph theory, then it is all done. You can solve any kind of problems, this kind of problems using this Bayesian network actually. So Bayesian network, you see, based on the problem nature, so we can successfully apply it in data mining, financial investment, for diagnostics, industrial control, not only for disease diagnostics, disease prioritizing. Suppose maybe there is number of symptoms, number of diseases, doctors are hesitating, basically that which disease, suppose multiple failures are there. So which we need to have some immediate attention. Suppose doctors are not in a position to take the decision. In that case, Bayesian network must be a much more powerful actually, because prioritizing that, okay, which things we need to take proper attention, obviously their probability will be more. In that case, it will be, I think, highly accurate, this using this Bayesian network. Once a group of experts taking some decisions, once there is some multiple failures in a particular patient, and they are yet to decide that which kind of failure need to be treated with much more care and at the earliest. If they are unable to take some decision, then obviously our Bayesian network could do some fruitful help in that particular case. Okay. Now this this is some Bayesian equation. Now see, already as I told, simply revisiting all these things, you know. So this is your conditional probability of A by B, A B by B. Now this is your joint probability. How we can write probability of A and B, probability of B into A by B, obviously equal to probability of A, B by A. Now see here. So this is, now see how we can revisit actually. So this simply our conditional probability formula using this total probability formula. So this is your conditional probability formula, you know. Probability of B by A. Obviously probability of AB divided by probability of A. Joint probability divided by marginal probability. Probability of B by A. Probability of A into B divided by probability of A. Okay. This probability of AJ, so BI, how we can write it? AB, probability of AB, how we can write it? Check. Probability of AB, how we can write it? We can write in this manner or not? Just check how I'm writing. So probability of BI into probability of AJ, BI. Probability of BI, AJ, BI. And what is probability of AJ? How we can write it? As already you have seen the total probability formula. This is the total probability formula. Probability of A, how we can write it? Probability of B1 by A of B1 into probability of B2, A of B2, like that. Plus probability of B3, A of B3, plus probability of B4, A of B4, like that. How we can write it here actually. So as I was mentioning here that now this Bayesian equation. So this was our total probability formula. So that means if we combine these two things, then how will we just check it? Probability of p by this. So that means so that simply this conditional probability formula. So how we can write using this total probability, this formula, how we can express it. Now let us quickly come to a simple Bayesian network model, so that may be much more helpful for us to understand. So here, what we want to do, so see, here we have some snowing. So these are the actually variables are congestion, tumbling, latecomer, injury, okay. And here this is our simply Bayesian network is given there. Okay, if snowing is there, it may lead to congestion, it may lead to tumbling, and if congestion is there, it may lead to latecomers, tumbling may lead to latecomers, as well as tumbling may lead to injuring also. Here, this we need to find out that probability of latecomer given that snowing. Okay, what is the probability? Probability of latecomer given that probability of latecomer be true given that probability of snowing equal to true. How we can find out? See. Just take it very clearly. So probability of, so this is our objective now. We want to find out probability of latecomer be true given that snowing be true. Remember, L for latecomer and all the symbols are using accordingly. S for snowing, C for congestion, T for tumbling, I for injury, like that you are using. So probability of latecomer be true given that snowing equal to true. So simply what is this conditional probability formula? So probability of L and S joint probability divided by probability of S. Now what is probability of L into S? That is the important thing. See. So here obviously this is a joint probability now. Probability of L. This is probability of L and S. So that means L depends on congestion tumbling depends on snowing. So all these variables now we are taking into picture. So based on congestion and tumbling, probability of this snowing, congestion, tumbling, and latecomer. What will be this probability? We can easily find it out now. So obviously, probability of snowing, this is the param probability, does not depends on any other. So this is probability of snowing. Congestion depends on snowing. Probability of congestion depends on snowing. Congestion depends on snowing. Probability of tumbling, see, tumbling. So here you are writing probability of tumbling. It depends on snowing and congestion. But is it like that? Tumbling depends on congestion also? No. Probability of tumbling depends on snowing also. So only yes. So C we can remove. Now this probability of this latecomer, obviously probability of latecomer should depends given that snowing, congestion and tumbling. This snowing, congestion and tumbling. Now see how we are writing. Check it. So probability of snowing, probability of congestion given snowing, probability of tumbling given snowing, and this is probability of latecomer. See, it is depending on this congestion and tumbling. So latecomer is not dependent directly on snowing. It is dependent on directly on the parent nodes, that is congestion and tumbling. So that's why we are writing this divided by probability of S. Now, if you have if you know all this probability, so easily you can find out that what will be the probability of latecomer be true once given that snowing equal to true. So again, so what researchers have done, actually they have revised this Bayesian network, whatever we have discussed in the last 2 hours. So they have actually improved or modified this Bayesian probabilistic Bayesian network into the concept of fuzzy set actually. And they have upgraded as fuzzy Bayesian network. Actually, this is another very much interesting concept, but very difficult concept also, because at the same time, you need to have some good ideas on this fuzzy logic and fuzzy set. As you have some ideas on this Bayesian network, but at the same time, you should have some very good ideas. Then only you can understand this fuzzy Bayesian network. But this is very much interesting. Actually, you know that sometimes, using the probability, whatever informations we are getting actually sometimes that may not be that much meaningful actually. So I'm not coming to the fact in details, but giving you some rough idea that if you can apply the concept of fuzzy logic using the Bayesian network, so that is going to be much more interesting. You can find out few papers are there, not that much papers, okay, using this fuzzy Bayesian network. And few papers I have seen, maybe interval valued fuzzy Bayesian network or some other fuzzy Bayesian network, but not that much. So huge opportunities are there if you try to understand the concept of fuzzy set, apply the same concept into the Bayesian network, obviously, then you may have some very good research scope. Actually, we are working on that currently. So that you may also try. You know the why the you know that there is a huge difference between the concept of fuzzy set and the concept of probability. Okay, although Bayesian network is working simply, probabilistic Bayesian network is working fine, but again, there may be some situations actually that there you need to apply the concept of fuzzy set into this Bayesian network also. So here you know that something some informations are given here. So actually, I will try to ignore this. So as I was simply mentioning, so you may, since you have some knowledge on this Bayesian network, so maybe you may go through the concept of fuzzy set, and later you may try to associate the concept of fuzzy set with this Bayesian network. Because as I was telling, that probability is for different purpose, and the concept of fuzzy leg, that is also a significantly importance, huge importance in the context of uncertainty actually. You cannot deny the contribution of fuzzy sets or fuzzy logic once you are dealing with the uncertain kind of natures. That's why researchers started thinking why we cannot apply the concept of fuzzy set also once you are solving the problem on this Bayesian network. Ample opportunities are there, and you can explore later all these opportunities. And today, as I focused more on this, so maybe I will not tell all these things. And but here few, as I was telling, that that easily you can explore it, that how we can, in fuzzy set, main concept is their fuzzy membership grade. So how we can fine tune your expressions regarding to the Bayesian network using the concept of fuzzy membership grade. You know that sometimes that something, suppose I am telling that that in a previous example now I was telling you something, that latecomer, how much latecomer, it is too much late, it is little bit late, it is not that much late. See, once I am telling some latecomer, that is it possible, latecomer means how, why, what kind of latecomers? Latecomers mean always is it 1 hour late, half an hour late, 20 minutes late. It is very difficult that simply to quantify the latecomer in that sense. There we need the concept of fuzzy logic. It may be little bit latecomer, more latecomer, latecomer, and I think like that only we can. That means if the concept is that latecomer time is, as I was telling, that not that much latecomer, it is very much latecomer. Okay, so that kind of situations, how to express using the concept of probability. Then you cannot do that anything using probability. Then you need the concept of fuzzy logic here. Okay, so that is the very real life situations actually that you cannot avoid, and that's why fuzzy logic and this Bayesian network are very much closely related actually. And now this is the applications of this Bayesian network. So as I was mentioning earlier, that you can apply Bayesian network in number of ways actually. You have seen the nature of this. Initially started with this Bayesian classifier, then competing with this Bayesian network. You can see the powerful nature of this Bayesian classifier or this Bayesian network. And based on that classification, obviously, that is important areas of this Bayesian classifier. And this Bayesian network you can apply for a number of purposes, medical diagnosis, as I was telling, fraud detection, data mining. So a huge importance are there for this Bayesian network. And you know that advantages of Bayesian network over artificial intelligence and machine learning, this is a part of obviously artificial intelligence, and here probabilistic reasoning we are working. We can do interpretability of causal inference. We can handle missing data. It can have powerful nature of Bayesian network. That for machine learning, so you need to train your model is that much number of sufficient data set so that it will work accordingly. But and if your data set is small, then your machine learning model may not work accurately. But this is the one of the main advantage of Bayesian network. So it may exhibit computational efficiency even with small data set also. So that is the most important thing for this Bayesian network, where it may, I think, may work much more better manner regarding the machine learning models. So it's already 5 o'clock, so we'll try to close here. So once again, thanks to the participants for having their patience to listen me over the last 2 hours. As you know, so already you have known, it is known to you that this is my email ID as well as this is my contact number and WhatsApp number. So if you have some quick questions, so I will take some quick questions. Otherwise, you can note down, and later also you can send me your queries. I know this session was a huge mathematical session.